Hi, everyone. Welcome to the Cyber Apocalypse. I am your host, Falcon Spy. We have a bunch of workshops ahead for all of you to participate and listen to. We do have a couple of presentations where there'll be a live Q&A after the presentation wraps up. So we'll start off here with our CTF Development 101, back to our basics. So this is with Macalaris. We'll have some opportunities for all of you to ask your questions at the end. We wanted to let you know that some of the members here that will be speaking are part of our content team, and they'll kind of give you some behind the scenes of how things work for about all the CTFs that we build out. So without further ado, why don't we bring on Macalaris, and he'll talk about building out CTFs.
Thank you, Falcon. So I'm really excited to be here and the content team. We've put a lot of work on the CTFs throughout the years. I've been doing this for 7+ years. So looking forward to a decade. And in today's presentation, we're going to be talking how we envision the CTFs, how we build them out, and for legal reasons, I need to tell you that this is an official Fallout fan presentation. These characters are not mine. I just use them because I really love the game. I mean, who wouldn't if you talk about another apocalypse like all the cyber apocalypse we've been doing for all of these years? If you've been a fan from the beginning, if I remember correctly, it was since 2021 a fresh idea to get people interested in cybersecurity learning, having teams learn together, fight together, and since this core idea of hack the box, training the next generation of offensive and defensive practitioners, we need to also involve how AI changes for operators. We are also going to talk about how we build CTFs and a specialized workshop on minute, I would say, the 10th most well-known vulnerability in web applications, the SSRF vulnerability, how much research can just go into what happens when a server chooses its own route. And we will be investigating how every new system creates fresh ways to get hurt. So, as you can see, I've been handling web exploitation mainly. That's how I started. I was building web scenarios and still am, and I've been helping the team to deliver the biggest CTFs that we hold, like Cyber Apocalypse, crazy numbers, 18,000 participants. Thank you for everyone for putting faith into coming into our CTFs, having a positive experience and sharing it. And I hope you do for this one as well. We've been cooking up, and it's a really, really great content. And I'll explain to you why. So, what I actually work on is the CTF portfolio strategy across community, enterprise, and government. And I set the technical direction for the quality bar throughout review, testing, and release gates. You also have a comprehensive end-to-end content life cycle, and we try to show to you how that looks like from the attacker side when we build for the same kinds of applications ecosystems organizations are trying to defend. CTFs have outgrown the niche. Events from 2023 to 2025 have nearly 3.5 times tripled. I don't know how to say it. and teams are up 3 times in these 3 years. And we had a recent CTF on site that I'm going to talk about in April. 33 teams at the Google offices in the UK played for 27 hours straight. 2 of the people won with 74 flags, while one business logic challenge stopped everyone, and I'm going to explain why. Both top teams cleared 74 out of 76 challenges. After 27 hours, 50 points separated them. I love how it comes to the number at the end, your team's performance. But if you're a beginner or you're just trying to learn, not compete, don't worry. We have CTF content that complements every skill level from beginner to intermediate to advanced to expert. And an intermediate tester usually gets through this machine in under an hour. The issue is that on that challenge, the agent found the right surface and kept sending invalid payloads. But the issue is that the difference is the feedback. People are more prone to notice the weird response and change course or deep dive into the system that not just the application code is attack surface, but also the underlying systems at the library level or the ecosystem level. Whereas to pivot from one architectural point to another needs to understand the contextual awareness that humans have, but AI doesn't. It will follow a rigid reasoning path. It will not improvise. It will guess. It will hallucinate. It will go on a rabbit hole and try to even tell you that what it's doing is correct, but it doesn't work for that reason or for that reason. And I have some interesting statistics for when we run the Neurogrid CTF event. So basically, we had last year on the Neurogrid event 1,500 teams across 36 challenges and 4 difficulty tiers. And the definition matters in the sense that AI augmented means a person is using an agent, not a bot left alone. And every chart following compares those people with people working without AI. So, with the same talent pool and the same challenges set, the gap opens at the solve. 70% of engaged AI users got one solve versus 44% without AI that got one solve. This is mainly persistence, not magic insight. AI augmented teams are more likely to solve something than human players without AI. At the top end, the solve rates almost meet. The time gap, however, does not. This is a very interesting insight that elite operators get about 4.1 times more leverage than non than human only, and AI gives a good operator someone that understands what they are doing to get more shots on a goal and dive deeper at the correct surfaces and logic points to follow through from one pivot to another with the contextual awareness that one meeting point requires the next in the chaining. We also expected the advantage to fade on hard challenges, but it grew instead. To keep the comparison honest, This is the whole population, not one expert versus one bot. AI gets more people across the line when we go to harder tasks. AI had the solve rate advantage on 84% of the challenge types, but there were three that were the exception, mainly the binary exploitation ones that required logical sequence that this leads to this, that leads to that, and the forensics one over messy evidence. The AI couldn't pinpoint what it was supposed to do. So as we can see on the 60%, humans solved it, but the AI did not. So these are the habits that are worth training. Turn a quirk into a foothold, understand the business rule and the necessity, and read the system's feedback. This is why we almost always give a localized environment for players to understand how the data passes through, for them to get a better sense on what they are supposed to do. And imagine this, we give out the source code on the web challenges, and still AI or humans have a difficult time solving. That's because the complexity of the exploitation process is what defines the difficulty of the challenge, not guesswork or AI slop. So that is how you direct AI instead of taking its first answer on faith. You need to be driving it. You need to understand what you're doing to get the best results. And as we know, with junior augmented operators, the AI will hallucinate. So when the AI hallucinates and the person doesn't understand what the goal is, or what they are doing, they will have a hard time solving something if they give bad directions, or they don't let the AI know how to proceed. The AI will just randomly throw invalid payloads, it will get nowhere, it will not understand the goal. So we allow CTF usage on this CTF and in CTFs in general. Please keep the rules in mind that we only allow cyber augmented teams and not autonomous bots. If you just burn tokens for the fun of it and you want to have the top placement on the board, if you know how to prompt it and find the business logic reasoning, or the creative exploitation, or the environmental awareness, that means that you could have also done it without the AI. It's just that the AI accelerates your solve rate and efficiency and time spent on something that you could have utilized your attention elsewhere. So keep in mind that there are cyber augmented teams in the CTF, they are allowed, autonomous bots are not. Before the case study on the SSRF, we will talk about how to design choices matter. It will explain how we give the target a world worth investigating. Because as we've seen, and this is basic psychology, me as a CTF player, I literally played some challenges on a random CTF, and after I became a content author, I couldn't play them because they seemed like they polluted my reasoning. That was before AI. I'm old now. When I was playing the content, I literally didn't understand why is there so much low effort done on the storytelling. If you give a good storytelling ability to the worlds that you create for hackers to play. They are more incentivized to follow through that if the storytelling is good, the challenge must be good. And we do both. And this is how we do it. So, if a scanner or a lucky guess solves it, or a copy paste of the payload, we haven't built a CTF, we have built a lottery. The hard part should be the chain. Real systems, realistic systems, evidence led steps, and enough depth to reward understanding. It's like how you have any kind of game. The game developers love when you explore outside of what you're seeing. It rewards you with items or experience or looting items for you to have later to make the pacing better. It's a lot of positives on doing this yourself, doing this with an AI and still understanding what you're doing. Because if you just point the AI to it, do nothing, then there is no point on playing either way. It's basically like cheating an exam. If you didn't learn about what the exam taught, then why even bother cheating about it? It doesn't help you, but it sets you back. So, of course, our worlds are not just decorations. We want to make the target feel coherent and keep people curious when the technical work gets hard. We've done amazing work with the team to create in these worlds. I want to give massive kudos to the product marketing team, the graphic design team, the community, the content team. Everyone bands together to give you a memorable experience, and we help put the visual identity direction into the challenges themselves. So they look pretty, they incentivize players to go the extra mile, all of that stuff. So right now, I'm going to give you some summation of what the storyline is about. Of course, the storyline is made with AI. We all know that, even the descriptions. But believe me, we think of the scenarios, they are humanly conceived. We don't get any success from just telling the AI, give me a description or give me a visual art direction. It's not going to look good and it will show on the content. So, this year's Old Crown is here because the signet, the crown, carries authority past its owner. Maylor, the king, showed the abuse, and with the next slides, I will give you 5 bits about where we meet the people that are caught into this world. So, in a world where it's medieval, you can see that the communities themselves aren't really communities. There is a lot of political instability, there is a lot of civil war, raiding going on, etc. etc. A godlike creature, a dragon, saw what was happening, Astrael, and now it went into the physical world to be a guardian and a punisher for humanity to get together and focusing on the common judge that is, if you misbehave, you're not worth being. So after the dragon swept to the skies of Valisar, we saw that roads were replaced with raids, grain was stored instead of stolen, and civil wars ceased to exist. So, forged with the relic of Strahler, we then move on to the Brine Signet, which lets one command travel beyond its author. Basically, it gives power into the king that inherits it in order to have law and reality check out on what needs to be done from a human viewpoint. And we have our past bad guy that now is dead, whereas King Maelor turned that machinery towards the bad stuff: purges, famines, crown disputes, etc. etc. So he dug down Crown Spire to the first mark beneath the asphalt, and it was hoping to bind the older authority into the signet so that he can change reality. He got very mad with power, he took it by force. He realized that dragons are a threat because they are the ultimate form of power, and this is something that he wanted for himself. So, Astrel then descended before the theft could be completed. With white fire, it swallowed Maelor, it shattered the Brine Signet, and drowned the asphalt. Now he's dead, but there is a whole kingdom that is waiting for a claimant in order to restore balance and order, because the dragon felt that that power must never reach human hands. So now the reality making is up to any human, and we need the right leader in order to have order and prosperity and stuff like that. Now, houses all over the kingdom raise banners, they mobilize kinetically people to start war again, since the Guardian, the dragon, left the physical world. And now we have the Prophet, which is Aaron Greywater from this why it's called Salt Crown, because he's part of the house that is born and their signet is Salt, and he wants to be a fair leader and put everyone together for the common enemy that you're going to see later on. So the dead king caused the fracture. Aaron Greywater wants to bring the disciplined stormbound force inland to end the war, refuse the throne, and with power stop the fighting and put enough limits to keep that power answerable. We have Kier, which is the underbelly's cutthroat. We have Alice, the queen of the quiet marches, where she's a cold priestess that has the ability to overtake minds, volunteers, wake up the dead, and with her undead army, she's marching inland with Maelor's inner workings. She will march into Crown Spire to change reality itself to the Dark Lord. We have Cassian Voltron, the Black Heir, which is whom is a claimant by blood of King Maelor. And then we have Seralyn Lyris, the Velvet Spider, that trades, and her power is bringing houses down with just gossip, with just information, and she's also a claimant of the spot. We then have the other forces in the fracture. We have the King's Guard left behind the Sir Garan Vos that did unspeakable things in the honor of an oath he took for King Maelor. We have Lord Damas, the Gilded Knife, that controls contracts, lifelines, coins, the whole trading system within Crownspire. We have Chancellor Valen Mar, which was the surviving witness of Maelor's and Sir Garanvos ordeal during the Asphalt White Fire. He was the one that understood how to, as a cleric, as a priest, how to say the correct words, the correct prayers in order to get going with King Maelor's plan, but he backstabbed him, and that's how he died, and the reality didn't change. Then we have Captain Rovan. He is disciplined war by contract, and we have the free clans with Sithra the Crow Eater, which is the Winter's Witness, whereas the free clans are going to be a very pivotal role into bringing everyone together in order to fight the common enemy that is the allies of the undead. Now, since Maelor is dead, the signet is broken, Astrail is missing. The question is, through the CTF, whether anyone can rebuild power without rebuilding the machine that made Maelor dangerous, and keep that thought as we go back to systems that trust the wrong route. Sorry, I really like storylines, so sorry for geeking out of you on what the storyline is. I hope we didn't lose a lot of people. But right now, I'm going to go on the technical workshop. How just a minute into 2021 OWASP, the 10th most well-known vulnerability. How deep can we go in that? The SRF starts with a simple mistake. The server fetches a route on someone else's behalf. If you follow that mistake far enough, it can even become code execution. So in this code, as we can see on the left, it is vulnerable because it's substring blacklisting, some bypasses, but 127001 is only one spelling of loopback. A blacklist loses before it starts. Maybe you've seen the how was the CTF called? Real World CTF 2020, if I remember correctly, the SSRF on GitLab. They were doing massive blacklists, and people still found a way to bypass those blacklists. And the correct way, as you can see on the hardened code on the right, you need to parse the URL, resolve it, and then validate the address and scheme you will actually use. Every value here reaches loopback. The raw string is a bad security boundary because you need to resolve it, then check the address against the ranges you refuse to touch. I'm going to explain more later on the DNS rebinding. Here, as we can see, the check and the fetch are two different DNS lookups. The gap is enough for a binding. You fetch the IP you approved rather than resolving the host a second time on the hardened example, because it's a time of check, time of use, because I can serve a DNS-A record pointing to an allowed non-private IP, and then when the DNS resolves again at fetch time, I can switch in milliseconds the DNS-A address to localhost, and I have full-blown SSRF. Another pattern is unsafe redirects. as we can see on PyCurl follow location, it's set to true. And as you can see on the payload example, I can host my own server, serve a redirect into the file protocol, and read etc. password. The first URL can be fine, but the direct can be toxic. A 302 is another request, so you need to give redirects the same protocol policy as the original URL with limiting the protocols in the redirect and limiting how many times you are allowed to redirect. Here we have disagreements between two routes. As we can see on the split brain allow list, we have URL lib3 URL parser and the requests, which is, if I remember correctly, URL lib by itself. If you send a payload like google.com /authority localhost, it gets validated correctly as Google. So if Google in parse URL.host is Google, it continues, but the requester fetches localhost. That's because localhost, google.com, is passed as a user info into localhost. So you are able to reach localhost because the URL parser and the requests URL parser disagree in what the URL and the URL components are. Since URL lib3's regex match for the URL components is very basic, if you inject a backslash, it will turn the rest of the string into junk data. So it will understand that it's just google.com, but requests will see that google.com is the user info and the real URL to visit is localhost. So the correct approach here is to use a single canonical parser. As you can see, I'm using from URL lib.parse anti-port requests because they're using the same RFC, the same URL parser. We have another interesting factoid here. I have a bunch. These are based on previous challenges that I did. If I remember correctly, this is from ImageTalk, a weekly challenge release. This is a classic parser disagreement. PHP can reject the URL while curl greedily finds a host and sends it by rebuilding the URL. So even if validation and fetching disagree with allow list, this has stopped protecting the destination because the issue is that PHP's parse URL and libcurl's parse URL are different engines with different host rules. This is from WeatherApp, a very well-known Node.js HTTP.cat serverless injection, which I think is pretty cool to talk about. As you can see here, the raw path input can become a second request line or even a third request line with HTTP pipelining. With serverless injection, you can send up to 3 requests on the same TCP packet, and it will be fine for the fetcher to fetch. So the correct approach here, instead of concatenating string boundaries inside the request wire, we need to build the URL as data with URL and URL search params. We do not assemble an HTTP request from string fragments. Node, back in that version, strips CRLF from header values. It does not give the request line the same treatment. So, the first write can use Latin 1, which is a single byte encoding mechanism, and this is where we have harmless looking characters, full width characters that can turn into dangerous bytes that bypass the CRLF injection by utilizing the single byte encoding mechanism and setting it 2 bytes. And the non-ASCII will fold into the HTTP protocol characters like the CRLF. These 2 Unicode characters look harmless, but in Latin 1, the single byte encoding mechanism, their low bytes become 0D and 0A CRLF, so the wire sees a CRLF even though the source string did not. So, right now, we were talking about HTTP requests talking to HTTP servers. What happens when SSRF opens a TCP connection, and how can we do that? The service on the other end decide what those bytes mean. So theoretically, we could also touch intranet microservice by just having an HTTP request. Let's see what I'm talking about. This is the hinge in the exploit. SSRF gets us a socket. Then the service on the other end chooses the protocol. So we keep this chain in view as we turn HTTP shaped bytes into a Redis write. So as we can see here, I forgot to add some disclaimer here. Okay, so basically, as you all may well know, when a Redis server with no require pass or bind gets a post request for CSRF or gets a host header, it terminates the connection. So from HTTP in PHP to SSRF to Redis, how can we bypass the host header detection that drops the request? In this example, as we can see in HTTP fopen wrapper.c, PHP sees the injected host header and suppresses its own. That matters because Redis never receives the automatic host line that would reject the header. This one fake header changes the whole request from HTTP communicating with Redis by overwriting the host header and putting the payload before the host header so that the payload is parsed through the Redis protocol, executed, and then it goes and finds the host header and terminates the connection. So Redis ignores the bad HTTP shaped lines like get/HTTP. Redis supports the line at host maquilardes, but what if we injected host, auto host suppressed, and as we can see, we can set PHP ready session to a value, and the host header comes after the CRLF injection. Redis ignores the batch HTTP sync lines. It runs the set command, then aborts at host. But the write has already happened. Keep this framing in mind for the next few slides. The resp is just length prefix tokens, nothing else. Once the receiver has one completed frame, it has a command. And it's done so by having an argument for how many verbs it will take, each verb how much length the keyword has, and it's kinda like a normal HTTP CRLF injected request. It can also communicate on that and binary mode. So how can we turn the URL into a TCP write? We are going to talk a bit more about the Gopher, how the path after /_ lands on the socket as bytes. There is no HTTP layer left to save you. The URL fetch is now speaking native Redis. As you can see here, we curl with Gopher on the Redis port set MAC-foo with a max time of 1, and the Gopher path became a TCP payload. Now on the verification side, we jump into Redis, we get MAC, and we see that the value was indeed set as foo, with no HTTP framing or garbage or whatever. Everything after /_ is written to the TCP sockets as bytes. There are a lot of Redis write primitives on to gain RCE. As we may well all know, authorized keys lazy parses and doesn't care about the config database backup being set as with junk data of the DB file name structure of the database backup of the memory store. Doesn't care about the header, the footer, whatever. It just checks that SSH.RSA and then the key exists there. So you might go and write an authorized key for yourself to SSH into the machine that you're pawning. Or through cron tab, where you can set a scheduled command to run every 1 minute with a reverse shell of your choice. As you can see below Redis encode, we have a very simple wrapper for how we can execute native Redis commands, like it's very easily written to be sent into Gopher and then Redis. There are other examples as well, like slave host replication with a module being sent from the slave to the host in order to get code execution, but that's not the point of Redis write primitives. We can also use MySQL, but the issue is with reconstructed packets to MySQL, it cannot read the server's challenge first. There is, as you can see on the right, the random scramble and MySQL native password in order to build the auth the auth token connection. It sends a greeting, it sends a handshake, it sends a challenge, and when the client responds, then it initiates the connection. This is built by default in MySQL in order to combat man-in-the-middle attacks. The issue is because there is plain auth on default and dev installs where you have the root user and no password, you can use the plain auth, and on the left, instead of back and forth with Gopher, you have a one-way write where curl streams the URL path as TCP bytes to the MySQL connection with root as user, plain auth, no password, no auth response or challenge response. So the login query can be forged in order to send blind SSRF, whereas you can use a time-based oracle in order to exfiltrate stuff from the database itself. Also, another Redis write that is very realistic in production environments is when an attacker writes the job hash, then pushes its ID into the queue, and to the worker, it looks like a normal application job. It cannot tell who created those Redis frames. So, what you have is essentially a Redis write where the application is using a job queue, and the job queue is something like serialized jobs that run every set amount or run when you invoke them, like get me a screenshot of that code. It will give you the screenshot. If you have the code to make the screenshot itself, it reuses the code that you have on your application. So by default, these job queues are deserialized in order to invoke them and get into, if an attacker does that, a deserialization gadget. The most basic example that I can share is the reduce magic method in cPickles, where you are able to create a gadget that will run a reverse shell. In PHP frameworks, it's used PHP GGC, a project with well-known gadget chains on frameworks that require a gadget chain, like going from the framework to the debugger to call sites that have magic methods where you are able to get code or command execution. In Python, it's much more simple because it just pick loads with a very simple payload, the reduce on a class method. You pickle dump it, you set it to the job queue through Redis or whatever. The Redis pick loads the data of the job queue, and you have RCE. But good news and bad news. Curl keeps closing parser bugs, and you should still upgrade it. This is not the application must own the allow list, the resolution, redirect checks. But one of the most heartbreaking news I ever got was that now URL decode, as you can see on the bottom, the escape hardening, the URL decode now reject null bytes at the decode time. So if you're doing cross-protocol smuggling, like TCP service smuggling via URL strings, it is effectively dead because in HTTP, you have CRLF as a delimiter. In other intranet microservices like PostgreSQL, MongoDB, whatever, the delimiter, the terminator of its value of the frame is null. So essentially, it's dead. Or is it? So this was showcased by some beautiful research that we saw online, whereas in Nginx config, you don't need a gopher trick or anything here. A user-controlled proxy target can do a technique that is called Nginx scheme hopping, where through Nginx you are pointing to the socket file itself with http://unix/path, where path is the CMD from Redis that you are injecting, and you can inject commands, Redis commands, through the socket file that will then be translated, since it listens on a local socket, to the Redis data storage itself. The network ACLs do not help when the proxy is already inside them. And a throwback to the classics, of course, active FTP lets the client choose the data connection target. You aim port at an internal service, and the FTP server becomes your TCP proxy. Old protocol features still make very modern bugs, whereas with the active port server, you choose an attacker chosen server that gets the TCP payload to replay. Then with passive port, you pick the port. Then with the port command, you bounce. If you have like the Civic Sync misconfig, you have if you have the flag prompt port promiscuous yes, you can still turn the FTP server itself into a writer for any reachable TCP service. So this is the end of the talk. I hope I didn't bore you enough. Of course, again, for legal reasons, unofficial Fallout fan presentation. Bethesda, please don't come after me. So think like an attacker, test like a scientist, and remember, AI helps most when the operator knows what to ask, what to notice, and what to verify. Thank you, everyone, for taking the time and listening to me. Please let me know if you have any questions.
Hi, everyone. I'm back. Thank you, Maclaris. If you have any questions, put them in the chat. We'll read them out, and Maclaris will answer. And if there's nothing, then we'll move on and thank Maclaris for his time. So, without further ado, we'll give it a moment or two to see if any questions come in, and go from there. While we're waiting, Mac, I'm guessing you've seen the Fallout TV series.
I have, but I think until season 1.
Okay.
I don't know. I like the game better.
Okay, I haven't played the game or seen the show, but I've heard great things about
both. Oh, come on,
so
please do it. It's the best.
I'll have to give it a shot. I know for people that have played the game, the ones I've spoken to, they're like, yeah, I just play this thing like I'm a pack mule. They grab everything, and then like the next thing I know, they just pull out this weapon that launches like a teddy bear nuke or something. I don't know. I've never played the game, so. But all right. We'll give another moment here. If any of you have any questions about kind of building out CTFs or anything that Maclaris had spoken about in his presentation, feel free to throw it in the chat. Otherwise, we'll move on.
Top 3 games. Cyberpunk. First game. Last of Us.
Okay.
I will treat the second one as part of the first one. Then we have Fallout, and then at the third place, Cyberpunk.
Okay. I don't think I've played any of those games. I think I have The Last of Us on my Steam list, but I've never played it. But that being said, so a question did come in for you, Makar. So this person's a beginner. They're pursuing mainly offensive security and red teaming. Sometimes they feel like they can't overcome anything. Doesn't really sound like this is particularly related to your presentation, but up to you if you'd like to answer it. What are some of the things that you can give tips-wise to people who are starting in the field and want to join the offensive security side?
I think that intelligence and self reflection can sometimes be a distractive thing because the self introspection tells you, yes, but they did that, yes, they had, yes, they didn't have. I think it's just being content that at the end of the day, you did what you could to overcome and learn something at your own pace, at your own necessities. Keep it like very small at the beginning. The first 1% is the hardest one. After you reach 10%, the rest is going to be great. And you will always feel like you could do better, but don't let that discourage you. Let that motivate you in order to move forward and grind and do this and do that. And very important, enjoy what you're doing. If you're overdoing it and you're not enjoying that, then you're doing something wrong. If you're not enjoying it and you are doing it, then maybe you should pick something else. Be very mindful to have a positive mindset to tackle these things. All of us started somewhere, and it's like for your brain push ups. Obviously, you're not going to go and without any training, anything, do 1,000 push ups. You need to train yourself and your brain day by day, month by month. Take things small at first instead of having a lot of things to solve together. Take one thing at a time, be pragmatic with your time and your abilities, and go from there. It's good to fail, as someone said. You learn more from failure. I have learned more from challenges that I never solved than I did when solving.
I got one for you. For people who might want to develop their own CTFs, what do you think is the most challenging thing in order to actually create good challenges for people to participate in of all difficulties? I think that information age we have right now with AI kind of put new creators in a deadlock because either the CTF participants don't care and they play just with the AI, so it's a bit discouraging, or they build it and it has a massive unintended, or they try to build something that doesn't have a natural flow. I can't understand how to put the words natural flow when it comes to service topology. Go from Redis, go to MySQL, go to this ACL bypass, go to Nginx. All of these things are an accumulation of you actually start doing something. The CV is not nearly as good as the projects you make. So don't build anything for an audience, build for yourself, because the experience that you're getting from there is much more valuable than any kind of feedback you're going to get. But of course, work with feedback, but take it with a grain of salt. It's not a personal attack. Of course, nothing is perfect. Perfect is a paradox because if you don't have imperfections, then you're not perfect. Sorry, I might have mistakenly said it backwards, but I hope you get my meaning. Nothing is perfect, especially the first try,
do more and more and more. Once you get the hang of it, move to bigger productions. We always like to have a helping hand. That's why I did a LinkedIn post on Nick Badalyan's looking for authors to help me build awesome stuff. If you have the knack for it, that you can make a memorable experience, either through exploitation, either through storytelling, or ideally both, I think that's the best. You have to, make it about your experiences, what you've seen in pop culture, in games, in anime. Nobody is born and knows that stuff. You need to be out in the lookout, to have fun yourself, to have fun interactions you can do with the challenge, and this is how you will succeed.
I think I got one more follow up. It looks like everything else in the chat isn't anything particular to CTF development, but for me, I have one for you. So I believe you've helped create, this particular cyber apocalypse as well as some of the others. So for this particular one that's coming up that everyone's going to be starting on tomorrow, without giving anything away, what do you think was one of the most challenging things that you had to do for the Salt Crown?
I think this year we put extra focus on the descriptions and coming up with memorable singled out scenarios for 70 or whatever challenges was definitely a big effort from our part and the people that we partner with. But I'm very hopeful that we have delivered a great result and everyone's going to have a great time playing it. So I'm open to any feedback. Let us know. We are very, very eager to hear from the community. Just on the tickets, please, don't make us debug AI sessions. Respect your time and our time. And yeah.
All right. Any final passing words that you want to give to everyone, Makalaris? Otherwise, we'll thank you and we'll move on.
Keep trying, keep researching, find a team, join the CTF. It's going to be a very, very good experience. So I hope to see photos of meetups, LAN parties. Literally, the only reason that we do it, aside from getting paid, is because we want you to spend your time well. That's why we're all here. That's why we put so much passion into our work and so much pride. Thank you.
All right, everyone, this was Makalaris. Thank you for joining us. We have coming up next is Lord Rookie, and they're going to be talking to all of you about when you can't read, you measure, and demystifying cross-site leaks. So without further ado, let's bring on Lord Rookie, and I'll turn it over to you.
All right. Thanks, Falcon. Right. Hello, everyone. Wait. I think it's the wrong screen. Wait. All right, cool. Yep. Hello, everyone. In this session, I will talk about an access leaks. I'm gonna talk about what they are, why they work in a modern browser, and how an attacker can perform them in practice. The main idea is an attacker often cannot read a document if they request the document on cross-site. So the browser will block that request and we cannot get anything from what we ask in the target. So in order to avoid that kind of protection, we getting blocked everywhere we go, then we use these attacks, access leaks, to determine whether our request is getting true or false from the browser response. And that's what we're gonna talk in this session. First of all, let's start on the browser. Oh, sorry, I haven't talked about myself. Okay, chat, sorry. Let me introduce myself properly. My name is Yuri Siraria, or you can call me by Lord Tuki. I work in Hack the Box as a content engineer. Previously, I was a pen tester for around 4 years, and most of my works is around web exploitation, challenge design, and also security research. Also, I'm a big fan of Maclaris. Thank Maclaris for the explanations, very long and deep. Nice. Okay, let's start by looking at how the browser loads the website. This is very important because the next slide we will talk more about this behavior. So we need to understand some bit of basics here. Let's start from the URL structure. First of all, we got a scheme. Scheme is usually HTTP or HTTPS. It's a protocol that the website uses to load a website you want to visit. Then we have a subdomain. This is not always there, but in most cases it's there. So it's kind of optional thing. We have a domain, and both domain and subdomain can be tied together into making a hostname. So we will call this hostname by right now. After that, we have a port, which is a number to a website. We have a path, which is what kind of resource we want to see on the website. And finally, a query parameters. Okay, so now let's talk about an origin. Origin is basically a combination of scheme, a host, and a port. So if one of these is not same, then it's considered as a different origin. Let's take an example here. As we can see, we got an origin which consists of HTTPS, this is the scheme, news.example.com, this is the host name or the host, and the port, which is 8443. So if we take a look in the below, we can see some example which looks exactly the same unless it have a path. And in origin, path doesn't matter. Path and query, it doesn't matter. The only matter is only three parts: the scheme, the host, and the port. So if we can take a look, the scheme here is the same. It's the HTTPS. The host name also the same, news.example.com. Here also news.example.com. The port also the same, 8443 and 8443. So this is considered as the same origin. However, if we take a look at the right side, we can see, although this looks almost exactly the same, it have the same scheme, same HTTPS, the same host name, news.example.com, and this is not important, as we say. But why does this considered as a different origin? If you might notice, this site doesn't have any specific ports. So when that happens, the browser will try to load into the port of the scheme. And by that, HTTPS port is 443. So the port is not matching with the example we have this. So that's considered as a different origin. And then let's take a look on the second example. We have the same scheme, but here the hostname is different. The hostname is cdn.example.com, while the origin that we have is news.example.com. This is also considered as a different origin, although the scheme and the port is the same. So in order to become a same origin, all of these three components must be exactly the same. If one or more of this option or this values are different, then it will definitely consider it as a different origin. Now, when we try to load a site in the browser, for example, we try to load news.example.com/article, the browser will not only perform a request to this only site. When the browser tries to load the site, the server will respond with a lot of document, an image, a font, a script, etc. And it might be across from different origin. So for example, the request of the page, it might be newsexample.com/article. It will also try to load assets, a CSS assets from the same origin. Okay. But in some cases, and most cases actually, the browser, the server will also try to load an origin as a request on different origin. We call this as a cross origin. For example, here, it will try to load a photos from cdn.example.com and also a JavaScript file from analytics.example.com. So when we put this on the browser doesn't only stop on this origin only. It will try to load all of the resources required for the website to be running as well. So why this is important, we will discuss this later. As one thing for sure, when the browser tries to load all of these cross-origin resources, it can show the content, but later on, the JavaScript cannot read the content. So the content is still visible to us, it's still loaded. However, we cannot access the data if we're using a JavaScript because it's a cross origin. And we will talk about it later. Here we will talk about a browser security. Especially, we're going to talk about same origin policy or SOP and also CORS. Because that is the two main protection in a modern browser that save us actually from dangerous attack, and also is can I say like the primary reason why access leaks exist. Okay, first of all, let's talk about the same origin policy. Same origin policy, or we so call it SOP, is the browser rule that limits how a script can load a data from another origin. Here, for example, we are coming from app.example, we are visiting the app.example, and we try to send a request to app.example2. Since both are from a same origin, which is app.example, we can read the response of this site, of this URL, or these resources. However, if we try from app.example, we try to access bank.example, and we try to get the response from it, the browser will block us. Why? Because it's a cross origin. And it will get blocked by protection, which is CORS, unless we state it otherwise. So in CORS is I can say like a whitelist mechanism that the browser will follows to determine if a website can load a cross-origin request or response. So when we try to send a request, the browser will send an okay, let's just move forward. The browser will send an origin header, like here, we are from app.example. We will try to fetch /API/me. The browser will send the origin header, and that origin header will be used to determine if it matching the request or the response or not. However, since here we are trying to fetch on our own site, so this will be the same origin. It's the same app.example. Thus, there is no need for browser to use the CORS header, which is the access control allow origin. Okay, so no need to do that because it's the same origin. Browser will have happily showing the response. But let's see on the second example. Here we are from app.example, and we want to load a request and response from API.example. Since app.example and API.example is from a different origin because the hostname is not matched, the browser by default will block the app.example to access the response. However, let's see how it works. First of all, the browser will send the request. It will add the origin header, which is the website we are currently on, app.example. And then the server responds with access control allow origin, which is whitelist to our site, which is app.example. So now when the browser see this specific header and the specific value, it try to match the origin header to the access control allow origin. If both same equals, then the browser can read the response and give it back to the app.example. So this is kind of whitelist, although in the previous presentation, in the previous slide, I talked about browser always block across origin to access the response from JavaScript. However, we can kind of make a tunnel, make a bypass from this by putting the access control allow origin. However, in most cases, let's see the third example. We are coming from evil.example. This is our site. Then we try to get information, get the details from the API.example. Again, this is a different origin. So by default, we cannot read the data. So the browser will send the origin header, which is evil.example. The request still goes through. So the request from evil.example still going through the API.example. The API example return with 200 OK. However, in this case, the API.example response doesn't include the access control allow origin. What does that mean? That means the browser cannot identify if our site evil.example is legitimate or not. And then if there is no this header, the browser will automatically block us to reading the response. So even though the request is success, we got a 200 OK response. So the server is happily accept our request and returning a data. But since there is no access control allow origin header, our site from evil.example cannot read the data itself. So the request just goes through, but we cannot get the data back. So that's the problem we need to solve. And here we go. We are going to use the access leaks. So based on the protection and the previous slides, we know that a browser can still load a request, a cross-origin request, but it cannot read the response from a JavaScript. However, it can still display the content of cross-origin request, as we have in this example. This example. So in this example, the browser can still load the request and show the response to us in the browser. It will render the response. However, if we try to check what kind of data is being displayed, we cannot do that. Okay, that's the problem. And now we want to know what kind of data is actually being returned by the browser, by the server in the cross-origin. Okay, now we are talking about access leaks. So access leaks is a side channel attacks in the browser. And what does access leaks, and what does a side channel is mean? A side channel attack is an attack that being used to get an information, but not reading the actual data itself. It will try to obtain an information by probing the behavior of an application. So the side channel is a way to determine if our request is true or false. So we can determine only that, true or false, true or false. So we cannot get the whole data, but we can get that kind of confirmation. Is it true? Is it false? Etc. That's very different than a normal bug in a client side, such as, let's say, XSS. With XSS, we can read almost all of the data of the web page. We can read the cookie if the cookie doesn't have the HTTP only flag. The XSS can read the whole page, it can read the response very well, etc., etc. However, if we are using access leaks, we cannot get that much data. But what we can get is a behavioral change of a browser. So we can know if a request is fail or success, if a request takes a long time or no, if a request have a different response than before, etc., etc. So we need to find and figure out what kind of, we call it primitive, okay? What kind of primitive, what kind of behavioral change we need to find to determine if the access leaks is working or not. Is it true or false? And since we doesn't read the data of a response, we doesn't trigger the same origin policy and also course. So we bypass those protection, although we need some extra step to determine if the response is right or false. So in order to do that, we need an oracle. This is not the database you know. This is a terms in a, I'm not sure if it's cybersecurity terms or IT terms. But an oracle is a way that we can repeat a way to answer similar question over and over again. So instead of getting the whole data out of the server, out of the response, we ask the server, is this correct? Is this false? If it's correct, we continue to figure out what kind of data is also correct, etc., etc. So we try to probe that one by one by one by one. It might take a long time, but at least it works. And for example here, for the attack skin we gonna use in most of our test case, we have an attacker side and a victim side. The victim side is already logged in, so it have a cookie, it have maybe a private information, it have a state, it have a document, sensitive info, etc. And we are coming from evil.com. Sorry, evil.example. This is our side, attacker side. So when we try to figure out the data, to exfiltrate the data from example.local, we might try to send a request. However, since we talked multiple times, we cannot read the response of a request. Why? Because again, SOP, course, whatever. So we cannot read the response of a site. We cannot get the sensitive information. We cannot get even if a user is already there or not, etc., etc. However, we can read the side effect of the request. This might include the timing, maybe the behavioral change, etc., etc. And we will discuss that later. So the important thing is here, we cannot get the response directly, but we can determine if our request is true or false based on the side effect of our request. I hope that easy to understand. I'm not sure if that easy to understand, but okay. And here we are. We are going to discuss about access search. XS search. It's a cross-site search by determination. To an extracted is an extraction principle to obtain an information from a site. So it's kind of pattern. It's like, how can we ask yes or no? But again, we cannot get the response directly. So access search is an attack pattern. We can say it as attack pattern. So it's not the wall attack. It's just a pattern where we can ask a server if our request is true or false, true or false. This is what we're talking before. So the idea is to using some sort of search feature. Here, for example, we try to access /search query, and this is the information we try to leak. If it's true, we might get a result, and if it doesn't true, we doesn't get anything. And this differentiation can make us information if our request is true or false. This is what we needed. But how can we actually know if it's success or not? What can we do about that? The request is being sent to the server, but how can we actually know if the request is success or not? That's the main problem here. We got a way to perform the request, but we doesn't know how yet to get the response back. And let's say we already know. The next thing we want to do is to prepare a list of questions, a list of candidates that we want to ask one by one. Then we will use a probing to ask the browser, to ask the server, is this query true? Is this data true? Or is it true or is it false, etc., etc. And then if we got a height difference, we can determine that the request is true. then we can save the state and we repeat the process over and over again. So for example, here we try to determine if the sensitive data is starting from HTTP C and then HTTP CO, CON, etc., until it got the full response. But it's just an example. It doesn't always be this flaggy thing. It can be something else, of course. Now, this is the primitive we want to use. So previously, we know that we can perform a search on a website. So now our task is to determine if the search that we have been performed before is true or false. And I will discuss several kind of primitive here. It's not all of it, of course. There's a lot more, but I will just explore the most common one. And the first one is error event. So in error event, we can determine if a resource is loaded successfully or not based on event handler. So for example here, we try to load an image from a target.example. Remember, we are on evil.example. So this is our cross-origin request. We try to load the image, and since we embed the image, we doesn't directly read the image data. This is fine. The browser can still run the request and also get the image back to us. And if the response is actual image, then the onload event is being triggered. However, if the request is error, for example, it may shown a different kind of content type, then the on error event will be fired. So this is our differentiator. You got what my point? So this is what makes it different. Okay, we got a true and a false condition, and we can use this to determine if our request is true or false. Here's the example of the vulnerable code. So the code says, if we are authenticated already, and we have the specific query parameter next URL, we can get redirected to any page we wanted. Okay, and then if we not authenticated yet, the page will return an HTML. Also notice that we also have an avatar.png, which return and content type of image/png. So now we can change this kind of setup to determine if our user is actually logged into the website or not. This is the attack scenario. Here is the attacker code. We will try to fetch the image using HTTPS target.example/login, and the query parameter is next URL. So the idea is, if the user is already logged in, then when we load the image using this link, then the server will try to redirect a user into /avatar.png, and it have the content type of image/png, and thus the onload event is triggered. Otherwise, if user is not logged in, the content type is text/html, and the on error event will be triggered. So this is our oracle, our differentiator. So we can now we can now get a simple information, whether a user is logged in on this site or not, using this image oracle. Okay. Then the second primitive is using a navigator behavior. So basically, most of the browser have a maximum redirect limits. This is kind of related with what Maclaurin said before about the maximum redirects. But here, the redirects is on the client side, in the browser side. So by default, most of the browser limit their maximum redirects to 20. So when we visit a site, for example, /account, we try to load, first of all, 20 redirects. Then we visit this last page. If this page showing the page, then we're fine. However, if the slash account is making new redirect, that means the redirect will become 21, and 21 is off limit of the most browser. The browser will throw an error. So this is what we're gonna do, what we're gonna use to determine if our request is true or false. So by using the browser behavior about the maximum redirects, if a redirect is exceeding 20, then an error will occur. Otherwise, it will be fine. So we can use this on our scenario to determine if a request is success or false. For example, we have a vulnerable code here. So if a user is not logged in, the server will try to redirect a user to /login. Otherwise, the server will just show the account page. So this is very simple, and I think most of the website using this kind of behavior. Then in our code, we will gonna use this kind of code. First of all, we will try to make a 20 redirect. So we might set up our own server that will sending 20 redirect on its own, and then it will redirect one more time to the target.example/account. And when the user is logged in, no new redirect is being occurred, and the account page visible, no error happen. This is true. We can now determine that if a user is logged in or not. Otherwise, if user is not logged in into the site, a new redirect will be happening, and it will become the 21 redirect, thus triggering the redirect error on the browser. So now we can now understand and obtain an information if a user is logged in into a site or not. The third primitive is network timing. This is very, very common being used in CTF, I believe, and probably in a pen test also. So what does a network timing do? So network timing is a way we can predict the way we can gain an information about whether a request is being processed long or short time. So we can determine if a request is being returned so fast. For example, this 40 millisecond, then we can determine that no much loading happening in the server side. That means the request is failed, or there is no data at all. Otherwise, if we send a request, then we got long time response. For example, here 180 milliseconds. This is 140 difference. We can determine if a request is fail or success. So basically, it's the same. We need two kind of condition, success or fails. But in this time, instead of doing redirects, instead of doing error handlers, onload handlers, we will use a timing instead. We will try to search and observe the timing of a request. So let's see the vulnerable code. Here, if a user is logged in and user have the ability to, if a user is not be able to read this, otherwise this is unauthenticated, user is not logged in, or user might not have the privilege to read it, the server will respond with 404, and the response will goes fast, of course, because no server-side processing will be happening. The response just end that quickly. However, if a user is logged in and have the privilege to doing the request, then the application will try to run this build quarter report function, which probably rendering an image, rendering a PDF, generating a lot of requests, etc., etc. So it will take a long time before it goes finished. And by that, we can determine by the fast and the slow response whether the request is being generated or not. We can use it as an oracle again. And from the attacker side, we can use performance.now. This is a browser API to determine the timing. We can use it before we send the request. So we set a time flag before the request begin. And then after the request is end, we will compare the response time. So we will, I don't know how to say it, subtract. Well, we will subtract the final time with the original time, with the early time. So we will know how much time it takes for a website to load it. And for example, if there is no access, if there is no processing happening in the server side, no heavily comparison things happening server side, then the response will return very, very, very shortly. And if there is some sort of server side processing, there will be, of course, a little bit. It will take a bit time longer than if there's nothing to do. And from this, we can then use it as Oracle to figure out if a request is true or false, if a user have a data or not. And the last primitive I want to talk is about frame counting. So previously, we talked about how can browser in a cross-origin request cannot read the data, right? It cannot read any kind of data from a target, from a cross-origin request. However, there is an exception using a window.lang. Using this API, using these options, these values, I think, we can get an information about how many frames, how many iframes is being loaded on the target side. So this is, for example, when we are a logout, the page show a very, very minimal public page. Maybe it's a landing page, maybe it's a login page, etc. And there is no much iframe to be happening there. We can check using win.lang, and we can see the amount of iframe that being loaded on that specific site. And if a user is logged in, a user probably going redirected to dashboard or something else, and when we use the win.lang, we can see that it have lot of iframes. So from this one, we can determine if a user is actually logged in or not using the iframe determinator. So for example here, again, when a user is not logged in, it will render an HTML about the login page. But if user is logged in, some sort of iframe will be sent to the user, will be rendered to the user. And we can use this to determine how much frame is being loaded on a site, on a target site. And here is our code. So we will use this code to open a new window, open a new tab in your browser, and then try to wait for a while so the page is loaded successfully. And after that, we will check the windows.lang, the properties of this newly opened tab, and we can check how many frames is being loaded there. So for example, we can set kind of decision. If a frame is being less than 3, for example, then it means the user is not logged in. Otherwise, if it's more than 3, for example here 5 frames, then it means the user is already logged in into that site, and we can determine based on how much frame it actually have. But again, it's only reading how much the frame is being loaded, not what is the content inside. We can just only get the number. Maybe it's 0, maybe it's 1, maybe it's 5, maybe 10, whatever. But not the data itself. We only get the number. So that's much pretty all from the primitive that I want to talk. We discuss about access search. Access search is a attack pattern. It asks a website, it asks a server about if this question correct or not, if this true or no. And with that question, we can try to determine if it's true or false using some sort of primitive. We have an error events, we have a navigation behavior, we have network timing, and we have frame counting. And absolutely, there are a lot more technique. There's a lot more primitive that can be used and be improve it and be used like creatively. But here I want to only discuss about this one. Sorry, this 4 or this 5. And bonus, guys, I've created a site to determine if you actually log in into Hack the Box site or not. Let me check. So this is the site. Currently, I'm logged in the Hack the Box platform. And if I click check, it will try to pop up a new window. As you can see, I'm logged in here. And the site will be shown that I'm logged in Hack the Box account. Okay, so it can determine if I'm already logged in or not. However, if we try to load a private window, let's see here, we go and then we check here. In this browser, I'm not logged into Hack the Box site, as you can see. And the site successfully determined that I'm not logged in into Hack the Box. So this is the one of the attack scenario we call Ting. And I think this one because it's not harmless. So I hope it won't hurt anyone. But it's still a cool technique. Maybe you want to show your friend, if your friend is logging into a specific site, you can use this kind of technique. If you want to check the source code, you can just read the HTML code here. It's only an HTML, so you can check if it's safe or not. And I will give it to you as a homework to understand how can I determine if user is logged in into Hack the Box account or not. You can just read the code and understand it. It's a very simple and very fun. And I think that's it from my side. Wait. And yep, that's it from my side. The last thing to be talked is, again, when we cannot read, we measure things. So when we cannot read the response of a browser, of a target we want to see, we will use a measurement to determine if our request is true or false. So even though we cannot obtain the full response of a site, we can still use this technique, access leak techniques, to determine some specific question and answer and determine if it's a true or false. So I think that's all from me, Falcon.
Thanks, Lord Rookie. Hopefully everyone learned a thing or two about cross-site scripts, cross-site leaks. We'll give an opportunity to have some people enter any questions they have into the chat. And if there's none, we'll continue on with our next presentation. So everyone, if you have any questions for Lord Rookie on anything that you just learned about cross-site leaks, go ahead and throw it in there. While we're waiting for that, Lord Rookie, I imagine you're also a part of the team that's making the challenges. So similar to what we asked Macalaris, is there anything in particular for the upcoming cyber apocalypse, without giving anything away, that you felt was challenging to create that you think a lot of people would enjoy?
Yeah, I have not much answer for that. I'm still a beginner. It's not like Macalaris is like the god of the content team. But surely there's some kind of challenging when designing the challenge, like how can we change one vulnerability to another vulnerability without being too like guessy, like maybe how it's realistically being built, etc., etc. And again, as Macalaris said, the AI, of course, we will use AI. AI is very good. But AI will be used for an enhancement, not the driving force. So when you may be researching, creating a challenge, etc. So the pure skills you have to understand the context of a challenges, how to make them insightful, how to make them realistically into a real life application, but also fit in the theme of the story is what makes me challenging. But surely there will be a lot of cool challenges waiting from across all of categories. Kudos to all content team.
All right. Someone from the chat wants to know if it's possible to bypass single origin policies through DNS rebinding. So are you able to talk a little bit about that?
Actually, that's a bright idea. I think it's possible. It's doable. I've seen a CTF scenario when user try to use DNS rebind to bypass the both SOP and CORS. It's absolutely doable, but there might be a recent browser protection that I think it's not that easier anymore. No browser have some sort of new protection. I'm not sure what kind of protection is that. I'm kind of forget, but I think there is a new update on browser that prevents that kind of attack. Not 100% though. I think I still know a one way or two way to bypass that just protection, but again, it's hard to actually implement that outside of the CTF context.
Okay. I don't think there's any other questions. So is there anything that you would like to part ways with before you sign off? Anything you want to give to the community before they embark on their journey tomorrow?
All I can say is have fun and good luck. Don't forget to communicate with your team. Then you use AI to aggressively keep learning, of course. Then just let AI do the things. You need to actually learn and improve so you can be a better and good person day by day. And I hope after you finish the challenges, you create cool write-ups, share it with our community, so you will also get a new friend and a new experience.
All right. Well, I'm going to keep you here for a second. Someone just entered a quick question in. So they're basically asking, how do we come up with limits used to check, for example, the network timing? So they're checking to see if it's anything greater than 120 milliseconds for a window length of greater than 3. Is it trial and error, or are there benchmark numbers that people can look at?
Okay, it's not. There is no like benchmark number that actually works on every scenario. You still need to measure it yourself. You need to trial and error. Maybe have a test account, test if how many the median of the error response. How much is the median? Maybe it's 550 millisecond, and then you then try to measure the median of the success response. Maybe it's 200 millisecond. Maybe it's 150 millisecond. And when you got the exact number that is maybe 80 to 90% accurate, you can then using that to your script. But again, it's depend on the network connection, the jitter, the lag, etc. So it might be hard to actually get the proper number, but it's still doable.
All right. Thank you, Lord Rookie. We appreciate it. And we'll get our next presentation loaded here. This presenter has elected not to do a live Q&A, but they're in the chat, so it's up to them if they want to answer questions there. But we'll welcome Heaps Don't Lie, or do they, with Wet Hands. Take it away.
What's up, everybody? I hope you are all good and ready to join our biggest B2C event, Cyber Apocalypse 2026. For this year, I have made a little presentation for you. It's called Heaps Don't Lie, or Do They? And as you can understand, it's about a heap technique called Use After Free, and we're gonna see how the same bug differs throughout libc versions. A few things about me. My name is Thanos Aridis. You may also know me as Wet Hands in the community. And I've been a content engineer at Hack the Box since 2021. I'm your pawn guy, you know, the one that makes the fancy TUIs that everybody hates because of the colors and the emojis. You can also find me on YouTube as Wet Hands, and I have my LinkedIn profile here. Feel free to connect with me and let the party start. The most critical asset when playing a heap challenge is actually the glibc version. In our examples, we're going to use this code, which, if you have played any heap challenge, is really familiar to you. It's a simple create, edit, show, and delete menu. Create actually calls malloc and it allocates memory. Then you have edit, which you can use in order to overwrite and edit whatever you have stored in your allocated memory. So we'll just print it on the screen, and delete will call free in order to delete your data. And why this is vulnerable? Because as you can see in the safe version, okay, create is pretty much the same. We have added a safeguard at edit and show that checks if the chunk is null. And the huge issue is here at delete. We see that in the vulnerable version, it only calls free and deletes the data, but there are some leftovers there. So in order to be safe, we need to actually call free and then nullify the address that we freed. I have made 3 binaries, Heaps Don't Lie 1, 2, and 3. They all use the same use after free primitive, and for simplicity, I didn't include many mitigations. We have NoPy, partial relu, and not stuck canary. The first challenge uses glibc 2.31, which, as we know, inside the TCAS there's just a raw pointer, so our exploitation path is to override the free hook with system, while Hips.ly uses 2.35, and right here we see a huge update. Instead of just having a raw pointer, right now we have this mangling stuff, so it takes a slot, shifts right by 12 bits, and then there is XOR. In our case, we don't have full ReLRO, we have partial, so we can simply override the free at God with system. And Hips.ly 3 uses 2.39, and we're gonna use pretty much the same technique as above. A brief theory before we proceed. What is stack and what is heap? Stack is actually the static allocation of memory. The sizes are prefixed, while in the heap, it gives more freedom to the user to allocate whatever size they want, edit them, free them. And because the user takes this freedom, that's why so many heap techniques exist. Right now we have a chunk layout, how it normally is. From this slide, keep in mind the offset at -0x8, which contains the metadata with P, M, and A, which is prev in use, is M mapped, and non-main arena. We can see it better here. We have allocated an object at offset 0 at this address. And we see at -8 we have the 0x41 right here. That means we have allocated 0x40 bytes, and the p bit is set to 1. That means the prev in use is set. How the TCAS works: if you have an allocation that is a small chunk, like smaller than 0x408, it goes inside the TCAS, while the large chunks go inside the unsorted bin. And all these bins exist for the size classes and to avoid consolidation. The cool part is that this is all intentional, the way free works. The developers want to have them all in one place, so it was easier and faster to allocate and free objects. This is a small diagram layout. As we can see, TCAS points to C, which points to B, which points to A, which points to null. And as we said earlier, the bug here is not nullifying this metadata. That means edit and show will have a pointer at the free data, which is not null, so it will contain a libc address. And what is our exploitation path? We're gonna leak a libc address. In our exams, we don't care about the heap. And we're gonna force the current version stored next value. We're gonna override the free hook or the free at God with system, and then call free binsh, which is actually gonna be system binsh, and give us cell. Now we're gonna get a brief review on what happened on the newer libc versions. As we can see, at 2.26 the TCAS arrives, nice. After that, at 2.29 we see that there is a check for double free, which does not affect us in this example. After that, at 2.32 we have the safe linking, the thing with the mangling pointers we showed earlier. And after that, at 2.34 we see that it actually removed the free hooks, making it impossible to override the free hook. Right here we see how safe linking encodes the root. So it actually added the protect pointer and protect pointer right here, which is actually this encoding. You take where the next is stored, then you shift right 12 bits, then you XOR it, and this is the encoded forward pointer you want. And at the latest versions of libc, we see that there are no hooks. They were totally removed. So let's start with our first challenge. We have Hips.ly 1, and what we're gonna do, we're gonna use the use after free bug we had, and with show we're gonna leak a libc address, and with edit we're gonna override the free hook with system and call system binsh. How we're gonna do that? We can actually allocate a huge chunk, which is 0x4f0 in our example. Then we're gonna use another allocation to avoid top chunk consolidation. We're gonna remove the first one, and after we delete it, because it was not nullified, it will contain a libc address that we're gonna leak like this by calling a show function. This way we're gonna find the libc base and calculate system. And now that we have libc base, we actually need to override the free hook with system. And right now, with a bit of heap feng shui, what we're gonna do, we delete the second and third chunks we have allocated. We calculate the free hook, now that we know the libc base. We write at the third chunk the address of free hook. We make two other allocations. Right here we actually see what we leaked, the libc address. And here we can see the free hook. Lastly, what we're gonna do, we're gonna edit the fifth allocation with system, which actually overrides free hook with system. And we're gonna call delete with binsh. So this will actually call free binsh, and the hook is overridden with system. So finally, we're gonna call system binsh and get our cell. As we can see here, our exploit works, so GG. Now for the second challenge that uses the libc 2.35. What we did in the previous example is write raw target into the tcas forward pointer, then pop free hook, write system and call free binsh in order to get cell. But this one does not work here. Why? Because the forward pointer right now decodes into garbage because it is unaligned, and the hooks do not have the same behavior as they used to in the previous versions. And this actually happens because of the safe linking. As I mentioned earlier, this is the mangling stuff for alignment, and how we're gonna bypass it. We make two allocations at index 2 and 3, both are 0x40, and then we delete the second one in order to leak the key for our XOR. After that, we have a known address right here where we want to land, and we have leaked the key. Right here, we're gonna find the encoded FD, and how we're gonna do that. First of all, we have no pi, so this is a known address. In the previous slide, we leaked the key. So by doing XOR, we can actually find the encoded FD because XOR works both ways. If you have two elements, you can find the third one. In this example, the free hook is pretty much dead, so we cannot use it. But because we have no rel-row, we have actually partial rel-row, we can still override the free at GOT with system. Or we can use the FSOP technique, which is a bit of an overkill here because most of the protections are disabled. But yeah, this could also work. This is similar to the previous slide we have seen. We have allocated an object. We see there are 0x500 plus 1 for the previn size bit. And right now, both here, the FD and the BK look the same. So it's gonna be easy to leak a libc address and find the libc base. One issue here is that one address is writable, but the other is returnable. So we need to align our payload. If we hit the second one, we see that it's a writable memory, but then we get an unaligned tcas chunk detected error and it hangs. But if we go to the previous one and actually fill it with zeros and system, we can actually override the free at GOT. We're gonna do it this way. And our exploitation path is similar to the previous one. We still need to leak the libc address, but right now we have two new stuff. We actually need to recover the key and find the encoded FD. Then we need to do the alignment in order to override the free at GOT instead of free hooks in the previous example. And then same way, we trigger delete binsh, which will actually call free binsh, which we have overridden with system. And here you can see the actual payload. And right here we see the output of our previous exploit. And last but not least, we're going to the third challenge. From 235 to 239, not many things changes, so we're gonna pretty much use the same technique. The new addition we have here is the tcas get n instead of tcas get, which actually does all this stuff. But then we still have the tcas get right here. The good stuff in our example is that it will always get inside the tcas get, so we can avoid this stuff. And we're gonna use pretty much the same thing as we did on the previous challenge in order to exploit it. And by using the same technique, we see that we get cell. The version 235 and 239 are different. We see that we kind of use the same technique there, in contrast with the 231 and 235 that used a really different technique in the way the pointers were handled. A small recap, we see that in 231, the target in our tcas was just plain text, and we had the hooks, so we overwrote the free hook with system, and we didn't need to abuse the GOT override. But in 235, we see that it was not plain text right here because of the safe linking, and we needed to leak the key, find the target, and then do all this pointer mangling in order to get the encoded FD. And instead of free hook, we use the free at GOT override with system in order to get our RCE. Also, we had this alignment issue right here that we needed to go one address before in order to land on the free at GOT. And at glibc 239, we use the exact same technique right here For the mangling, same stuff for the free override, and it was even easier because we didn't have to align because of the put car. So we see that between these three versions, last two were pretty much the same, but the huge jump was between 231 and 235 because it added the safe linking and replaced the hooks. So a small tip from me when you deal with heap challenges, first of all, you need to see what files you have. For example, we have this libc version. The challenge has pi, full relo, canaries, or whatever. Then take a look at the allocator. Does it use realloc, malloc, ptmalloc2, whatever, and check at the certain libc version how does the malloc behaves. Also, the same stuff with free. And apart from that, always check what you actually leak, where you can write, what you can overwrite, and keep in mind all the freedom that the developer gives you, like how much you can allocate, what you can free, is there a double free, a safe linking, a use after free, or any keep feng shui or known house of whatever. So in order to wrap things up, heaps don't lie, or do they? So the heap actually tells the truth, but your different libc version and malloc might not. So always keep in mind to check the malloc code and what insertions and deletions happened there in order to understand what of the old techniques you can use and create your own exploitation path to get RC. So this was my presentation, guys. I hope you learned something about the heap and enjoyed it. I want to wish you good luck in the competition and have fun. Bye.
All right. That was a recording by Wet Hands. They're currently in the chat. So if you have any questions for them, throw it in there. We'll welcome to the stage next is xClown. Same bytes, different parsers, why HTTP servers and proxies disagree. This is also pre-recorded. They're in the chat as well, answering questions. So we'll kick it off to xClown and their recording.
Hey everyone, welcome. Today we are going to build the foundation for request smuggling. Some of you might be thinking, isn't this an old bug? Don't we already have a lot of blogs about it? And yes, you are right about that. The classic cases are old, but the request smuggling is very much alive. My recent research shows the same thing. I can't share the research yet because some teams are still working on the fixes. So this crash course is not about the whole topic. We won't memorize a few payloads, but we will learn the base idea and then use it to understand a different cases. By the end of it, you will know what request smuggling is more than just classic content length and transfer encoding. And let's start. Before we begin, a bit about me. I'm Rajat, also goes by the name xClown. I am a senior content engineer at Hack the Box for the past 4 years. I build CTF challenges and machines across different categories. And I also do independent security research. Here is the whole game plan for today. First, we look at one normal request and read exactly what the client sent. We just want to understand what the client is sending. Next, we compare every system that reads the request. Where does each one stop? If one component builds a new request, what does it send forward? Then we follow anything left behind. It could be extra bytes or a connection that is reused. We ask if it affects the next request. And again, do not memorize the payloads, just try to understand where the split or two components disagree and what happens next. Before we even break anything, let's make a normal HTTP request and try to understand what happens behind the scene. A client sends a request for the score pages in this format. The server reads the request and sends a response back for the score page. Here, it says everything worked and returns the result. So the basic flow is simple. Request goes in and request comes back. But the modern web traffic usually has other system in the middle. Let's add them. Now, let's make the path more realistic. On the left, The client creates the request. It could be a browser, an app, a script, or testing tool. Next comes the front end. We are using a box to keep it simple, but it could be a CDN, a WAF, a gateway, or several systems together. It can read, filter, change, or translate the request. Its parser decide what the byte mean and where does the request end. The backend receives what the front end sends and parses it. Then the app runs. So even this simple path has more than one readers, and the backend shouldn't trust everything the front end is forwarding it. If both readers choose the same ending, everything is fine. If they choose a different ending, some bytes can left behind and read as a new request. That is where request smuggling begins. We keep asking two questions. Where did each reader stop and who reads the leftover byte next? Okay, this is a lot of text, but we only need a few landmarks. Let's read one normal HTTP 1.1 request. The blue markers shows where the each line ends. We call this CRLF or carriage return and line feed. It is sequence of two special bytes. The request line and every header line ends this way. Now look at the pink empty line. The first CRLF ends the header sections. It means there will be no more headers after this and the request body will start. Content length says the body is 8 bytes. The reader takes the exactly 8 bytes and stop after the final R. The body does not need another CRLF. The next byte can already start a new request. Now let's read the same request from top to bottom. The first line tells the server what to do, which path to use, and the version. Next comes the headers. Here they give us the target host and the body length. And these are just two example headers, and there are a lot of headers which are defined by the RFC, or developers can set their custom headers as well. Moving on, then we reach the empty line. It tells the server that the headers are finished. After that boundary, we can have a body. Here, q equals to parser is the body. You just have to remember this format for now. Now we do only the math on this slide. Content length tells the reader how many body bytes to take. Here the value is 8 and each character is 1 byte. The count starts after the empty line. We count q equals and the parse word that gives us the 7 bytes. The final R is the byte 8. The reader stops right there. Anything after byte 8 is outside the body. If the connection stays open, the byte 9 may start the next request. So a different counts mean a different request boundary. Here is one idea that often causes confusion. A connection is not the same as a request. Think of the connection as an open lane. Request 1 is the first message using it. When the request 1 ends, request 2 can use the same connection. The client does not need to open a new connection every time for each request. Request 3 can follow 2. The request sits one after another with a clear boundary between them. Now the risk is easier to see. Get one ending wrong, the leftover byte from one request may become the start of the next one. Before we call a connection shared, we need to separate two sides. On the left, the front end accepts connections from clients. On the right, it has its own connection to the backend. These are not the same sockets. User A connects through the client socket CA For this request, the front end chooses the backend socket B17. CA and B17 are two different connections joined by the front end. Now, user B arrives through a completely separate client socket CB. The front end can send B's request through the same backend socket B17. So A and B never shares a browser connection. The shared part is the backend side. This matters because bytes left there by A may still be waiting when B's request arrives. Now we have reached the main idea. This is one stream of bytes on one connection. I drew it twice only to compare two views. We did not send two requests. Look at the green proxy view. The proxy keeps everything including the get/admin inside the body. It stops on the far right and sees the whole thing as one request. Look at the red backend view. It ends the body earlier at the red marker. The bytes after the marker looks like another complete request. Those bytes do not disappear when the connection is reused. The proxy sees one request and the backend sees two. Even if the connection is not reused, those bytes will still be processed by the backend. And in a nutshell, that's the desync. Once you understand the split, we can study four ways to reach it. First is length. Two readers calculate different body sizes. Second is framing. They disagree about which byte and chunk data. If you don't understand what chunk data is, I will explain it later. Third is early exit. A server answers before it reads the full body, so bytes are left behind. Fourth is translation. A gateway receives HTTP2 or HTTP3 request, and then it builds a new HTTP1 request for the backend. These four are not the full list, and the bytes may change during translation, but the underlying method in all are the same. Mark the boundary, then ask what the reader receives. A different boundary explains the bug, but a weird response is not enough to prove impact. We must show what the extra request can reach or change. First, it may capture part of another request, including a cookie, a token, or body data. Second, it may reach the path that the front end should block. We can prove this kind of bypass using our own account. Third, it may change the shared state. Another user could receive the wrong response, or shared cache could store our content. A timeout or strange reply is only a clue. A strong report shows the exact security boundary we crossed with the bug. Let's use a real case to learn the idea. This bug was found in OpenWRT's HTTPD server, and the fix is public. Both sides receive content length set to 0100. The split only exists if the system in front forwards those exact digits. The HTTP rule uses decimal or base 10, so this reader sees 100 and waits for 100 body bytes. But the vulnerable server used a generic number helper. It saw the leading 0 and guessed it is octal or base 8. So the same digit becomes 64 for the server. Now, look at the gap. The upstream still sees 36 body bytes, but the backend sees those bytes after request 1. If they form a valid HTTP or the HTTP connection is reused, the backend may read them as request 2. Here, the request has content length set to 10 twice. Both values are the same, This does not normally mean the body length is set to 0. The 0 came from a bug in Waitress. A careful front end can compare both values, they match, so it uses one length of 10 and reads 10 body bytes. The vulnerable Waitress version joined them as 10, 10. Its number parser could not read that, so Waitress silently used 0. Now, it believed the request had no body. The real 10 body bytes were left on the connection, and then later, those bytes were treated as the next request. The safe rule is simple. Either you can reject the duplicate length or confirm that every value is the same and keep only one. If parsing fails, do not turn the value into 0 and continue. Content length gave us one total for the whole body. There is another way to define body bytes using chunked encodings. It works in smaller pieces. Each piece begins with a size written in hexadecimal or base 16. Here, the first size is 5. So we take the 5 bytes from the word hello. We repeat the same move, the size is 3. So we take the next 3 bytes, HTB. Then we consume its line ending. Now, the size is 0, which means there is no more body data. Extra headers called trailers can appear here. This example has none. So the empty line ends the chunked body. The application does not receive the sizes or these line endings as body data. It only receives hello HTB. Keep the 0 boundary in mind because the next bug is about 2 parsers stopping in different places. A client can send a request with both content length and transfer encoding. According to RFC, transfer encoding takes priority over content length. Multiple proxies either reject the request or removes the content length if transfer encoding is present. That's the safe behavior. We are looking at a broken chain. The front end follows content length 43. The 0 chunk takes 5 bytes on the wire. The GET request after it takes 38 more. Together that's 43, so the front end sees all as one request. The backend follows the chunked rule instead of the content length. It reads the 0 and stops after the 5 bytes. Now the 38 GET bytes are left behind and are treated as the next request. If the connection stays open, the backend can read those leftover bytes as request too. Let's take a look at a recent issue around chunk extensions. But before that, we first need to understand what a chunk extension is. When you define the size for a chunk, there is an optional metadata field called chunk extensions you can also define. For example, the extension is sig equals to ABC for this specific chunk. The first CRLF ends the size line and then comes the body bytes and then final CRLF to end the chunk. Now let's take a look at the malformed input. where we have the size 2, and then we have the separator, which is also known as the extension start. And instead of a CRLF, we just put a bare LF and then body bytes and then the ending CRLF. Now, this bad input alone is not smuggling. We need another reader. The green side is conditional. If the system in front reads the single LF as the end of the size line, the 2x becomes its 2 data bytes. This depends on the front end and the real deployment. The red side is verified. In the direct echo test, Castrol kept the LF and XX inside the extension scan, then waited for the later CRLF. Now, the two reader plays the boundary differently. In a compatible chain, that different can expose a hidden request. The official fix checks CR and LF together and rejects an unpaired line ending. That is the safe rule: reject and close instead of guessing where the chunk ends. This problem can begin inside one server. We do not need a proxy to create it. Imagine a client starts a 20 byte upload on one connection. At this point, the body has only started arriving. After a few bytes, the server already knows the authentication failed. It does not need the rest of the body to choose its response. So it sends the 401 status after reading only 3 bytes. It can be 3, it can be more, it can be less. The application is done, but the connection is not clean. The other 17 bytes may still arrive. Sending the response did not remove them. Before reading another request, the server has two safe options. It can read and discard the remaining bytes within a safe limit, or it can close the connection. The unsafe choice is to reuse the connection immediately. The early response is not a bug. The bug is starting a new request while the old body bytes can still arrive without draining the connection. Now, let's replay a public Apache issue. First, Apache receives the first part of the request body. Then the client pauses. The full body has not reached Apache yet. Apache tries to discard the rest of the body. An error happens during that step, and Apache sends a response. More body bytes can still arrive after the response. Some of those bytes can be shaped like another HTTP request. Apache left the inbound connection open. That was the main bug. The later bytes could be treated as a new request behind a streaming front end, and this can create a server-side desync. So far, we have worked with HTTP1. We read a text request line, the header, then the body. In this post request, the 5 body bytes are hello. HTTP2 carries the same meaning in different format. Header frames describes the request. Data frames carries the body. The arrow is only comparing two formats. It does not mean every HTTP2 starts with HTTP1. The end stream flag tells us the client is done sending this request. It is a flag on the frame. It doesn't have its own frame. Let's unpack one HTTP2 request. We start with the green header frame. It says the method is post, the path is slash submit, and the content length is set to 5. The body can come in more than one data frame. The first frame carries the character HE, and the next frame carries the rest of the character. Together, they give us 5 body bytes. The final data frame also has an end stream flag. That means the client has finished sending this request. If there were no body, the flag could be on the header frame itself. Put those pieces together, it is still a post request on the slash submit route with the body hello. The request meaning is the same, only the wire format changed. HTTP2 already give us frame boundaries, content length, can still tell us how large the full body should be. In round 1, it says 5. The data frame carries 2 bytes and then 3. So the length check passes because both of the values are the same. This does not prove the whole request is safe. It only proves that the two body count matches. Now look at the round 2. The content length still says 5, but the data frame carries 2 bytes and then 4. In this case, the content length and the length of the data frame is not equal. So the HTTP2 message is invalid. A streaming system may have sent bytes forward already, but once it sees the mismatch, it should stop the stream with a protocol error. Before we translate anything, let's talk about why even use HTTP2. A browser can run several request streams on one connection, so it does not need as many connections. It also compresses repeated headers, that means less overhead and often less delay on the client-facing hop. But HTTP2 is not automatically secure just because it's newer and faster. Now, why would a team stop HTTP2 here? Their CDN, load balancer, or reverse proxy can speak HTTP2 to the browser while the app server behind it stays on HTTP1. Maybe the backend software is older or the internal setup is much simpler to run that way. They still keep the client facing benefits, but this middle system must validate before translating. Here, content length says 5 and the data frame also contains 5, so the count matches. Next, it builds a new HTTP1 request. It keeps the slash submit path, takes the authority value, and write it as host header. It also writes content length 5. The new request must have a one clear body boundary. The backend receives the new request. It reads hello as 5 bytes body using HTTP1 behind the edge. And this is automatically not a bug. The danger starts if the translator accepts a bad HTTP2 message and creates the wrong HTTP1 boundary with it. Now here is the broken version. The HTTP2 field says the body length is 0, but the data still arrives. That message is malformed and should be stopped. But the unsafe vulnerable version misses the check. It writes the content length to 0 in HTTP1 request and it still forwards the data bytes. The HTTP1 backend trusts the 0 for it. The request 1 ends after the headers. The bytes after that already forms a valid GET request, so the backend can read them as two requests. This is the simple version of the native bug class. And that is h2 dot content length. There is no magic header. A malformed HTTP2 request got through the translator, and the new HTTP1 boundary exposed the extra bytes. First, a quick HTTP2 recap. It runs over TCP with TLS, and header frames describe the request. Data frames carries the body, and the end stream flag tell us when the client is done. HTTP3 keeps the same request meaning, but it runs over quick. We still have headers and the data. This time, the request ends when the client finishes sending on the quick stream. There is no end stream flag. If content length is present, we count the data bytes and compare the two numbers. If content length is missing, there is no promise number to check. The middle system can count while request is arriving. As soon as it knows the number do not match, it must stop forwarding the bad message. Content length promises 5 bytes, but this HTTP3 stream carries 7 data bytes. The sixth byte is enough to know the count cannot match. A correct path stops forwarding and signals HTTP3 message error. If it was streaming, some earlier bytes may already be downstream. The unpublished translator pattern does the opposite. It writes content length to 5 in HTTP1, but forwards all 7 bytes. The backend trusts that 5, it reads 5s of the current body and leaves exactly 2 bytes at the next request boundary. Those 2 bytes are not a request, they matter only if later bytes complete valid HTTP and the backend connection is reused. But this showcases that the bug is not specific to HTTP2, but anything that translate one protocol to another. Because this case is still private, these are the results we expect from the controls. The baseline keeps both part of the bugs, the length mismatch and a reused backend connection. Control A removes the mismatch. The promised length and the real length now match, so the leftover byte should disappear. This checks the cause of the split. Control B keeps the mismatch but closes the backend connection. So the leftover bytes may still be there, but the socket cannot pass them to another user. They also still need a valid HTTP byte to become request 2. So control A tests why the boundary split happened. Control B tests one way the leftover byte could reach someone else to increase the impact. Each control changes only one part, so we can understand what its results mean. Now we know how a split can happen, but how can it reach another user? Keep the picture simple. One front end and one back end. User A sends the trigger. The back end stops in the wrong place, so byte stays on the connection. The connection is now dirty, but no other user is affected yet. The front end puts that connection back into its shared pool. The pool is just a group of backend connection it can reuse. Now, user B, a different logged in user, sends a normal request on another client connection. The front end may choose the dirty connection B17 to forward user B's request. If user B sees something only user A could, we have cross user impact. The logs should show both users on B17 closes that connection and repeat. If the effect disappears, connection reuse was the bridge. Now let's see why a shifted response can be dangerous. In the normal flow, request A gets response A. Browser A receives its own data and its own cookie. After the desync, the response queue moves by one place. User B sends a separate request, but the next response in the queue does not belong to user B. Response A now lands in browser B. Some shifted response include a set cookie header that could log one user into another user account. And in this example, we are using just two users, but imagine if there are hundreds and thousands of users, each one will get the wrong response. Let's pause and bring everything together. These are the four patterns we covered today. These are not all the possible request smuggling, but all of these have the same underlying cause. First is length. Two readers turn the same length value into different body sizes. Second is framing. The reader gives the same chunk byte different meaning, so they'd stop at different markers. Third is early exit. One component answers before it reads the full body, and some bytes are left behind. Fourth is translation. A gateway turns HTTP2 or HTTP3 request into HTTP1, or you can call it HTTP2 or 3 downgrade. The causes are different, but the result is similar. Two components end up with different request states or even different connection modes. The Pingora upgrade bug is a good example for that mode split. A shared connection pool can carry that dirty state into another request. The pool is not the fifth parser bug, it is one of the way the bug can reach someone else. I won't read everything on this wall. These are the public bugs with fixes. Just watch how the same boundary mistake keeps happening and returning in different codes. For example, the waitress HA proxy had another length bug, and then Netty showed that translation could create the split too. And then we have Apache's bug that came from early exit. Even in this small set of examples, even though each of the bug is different from one another in terms of exploitation and the reason it occurs, but the underlying cause is the same, where two components disagree where the request should end. This research did not start with me. By 2005, the core idea was already clear. Two HTTP components can disagree about one request. In 2019, new research showed why those old parser differences still mattered in modern applications. In 21, HTTP2 made the map bigger, translating a request into HTTP1 became another place where boundary could change. Then browser-powered desync showed that a normal browser traffic could also carry the attack. HTTP Guardian took it further by comparing many real implementations automatically. That made parser difference easier to find and repeat. The important part is how the question kept growing from one clever payload to full path around the request. Like in how many ways one can make two components disagree about the same request. If you want to go deeper after this workshop, these are the great places to start. Use this ladder to keep the claim honest. Strange parser behavior is useful, but it doesn't mean it's a security impact or a security bug. Here is the first trap. The trigger works when we go straight to the backend. Real traffic doesn't directly go to the backend in realistic deployments. There are multiple proxies or checkpoints, which also parses the request. And if any of those components rejects or rewrites it, we may have something to compare, but we may not have proved a desync on the deployed path. The second trap looks more exciting. Client A sends 2 requests on one connection and get 2 replies back. That shows the backend processed the 2 requests. It does not show that another user received anything. So it stopped below security impact, and that is just a weird or a strange behavior done by a parser. For cross-user impact, use a distinct logged-in user B on another client connection. It can be a separate script, it can be a separate Docker containers, and shows an effect only A could cause. That effect might be A data reaching B, a blocked request getting through, or the wrong cache entry changing. Then prove the socket path separately with connection logs and run where the socket is closed before B sends. Stop at the strongest label. The evidence supports. A smaller honest claim is easier to trust. So where should you go from here? I have 3 routes for you. First, try one guided lab. It is the fastest way to watch 2 readers disagree without adding too much theory. Second, try to read some of the RFC for proxies or HTTP 1 protocol and 2 and 3, or you can use AI to parse all these and find you conflicts with each or places where the RFC leaves the decision in the hands of the developer. Third, build your own lab. Capture what both sides receives and repeat the 3 tests we just covered.
Whoops, had the mic out of the way. All right, that was xCloud. And that should wrap up the rest of our presentation workshops. Thank you, everyone, for joining us. The Cyber Apocalypse CTF Salt Crown starts tomorrow in about 21 hours from now. You can take a look at Discord. You can see when it starts in your local time zone. You can go to the CTF page and see when it is in your local time zone as well. If you're looking for teams, feel free to join us on Discord as well. You can post in the Find the Teams channel, and hopefully you will have an enjoyable cyber apocalypse. And we can't wait for you to all get your hands dirty in the various challenges that our teams have created for you. And we'll see you tomorrow.